Hi everyone. In this video we're going to go over some parallel circuit problems specifically related to electric energy and power. So this is a question from a past Regents exam, and it says 3 lamps are connected in parallel to a 120 volt source of potential difference as represented below. Part A asks us to calculate the resistance of the 40 watt lamp. As always, I started by annotating. I circled my numbers and units, 120 volt, 40 watt, and I boxed my keywords. For me, this was just potential difference because it's going to help me figure out what 120 volts is supposed to be. And then I underlined the unknown, which is resistance. It's important to know that you're looking for the resistance of the 40 watt lamp specifically. So when I list my variables, I'll call that R1, so I know it's for this branch and not the total, or for this light bulb or this light bulb. Okay, so I'm going to be listing up my variables. V is equal to 120 volts, P is equal to 40 watts, and I'm looking for R1. I look at this formula on the reference table, and it's kind of long, but remember that when they have a bunch of equal signs, you can pick and choose whichever 2 sections of the formula make the most sense for your problem. So I know power is 40 watts, so I'm going to do P equals, and then I'm going to pick whichever one of these 3 makes the most sense. So for me, I have V and R listed, so I'm going to pick this last section. So P is going to be equal to V squared over R, and I'm just going to totally ignore these 2 things in the middle. I labeled it R1. Of course, in this formula, it's just labeled R. That means it can be any resistance, as long as you're consistent. So as long as I'm only doing stuff that relates to the 40 watt lamp specifically, the formula will work. Okay, now I'm looking for R, which is in the denominator, which can be challenging, so I'm going to try to use the pyramid method. By that I mean I'm going to put whatever's at the top of my fraction on the top of the pyramid, whatever's on the left in the left section, and whatever's on the right, bottom right, goes in the bottom right section. So this is how the formula fits into the pyramid. The point of this is so that I could theoretically cover up one of these letters or variables that I'm looking for, and it will tell me what it's equal to. So for example, I can cover up P, and it's equal to V squared over R. I could cover up R, and that's equal to V squared over P. I could even cover up V squared, and it will be equal to P times R. So when they're next to each other, that indicates multiplication. When one is on top of something else, that indicates a division. So my new formula is going to be R equals V squared over P. You may realize at this point that we kind of just switched the places of P and R. That is only okay in this situation. So when I have something equals a fraction, I can switch the denominator of the fraction with this first variable. But that doesn't mean that I can always just swap 2 variables whenever I want. It's just specifically in this format. Something equals a fraction, the denominator and that original variable, these 2 can switch, that's fine, but I can't switch R and V. I can't switch P and V, if that makes sense. Okay, so this is my formula, R equals V squared over P. Then I can just plug in my numbers. So I have R equals 120 squared divided by 40, and that gives me 360 ohms. So that is my answer to part A. Part B says calculate the amount of electrical energy dissipated by the 100 watt lamp in 1 minute. I'm going to annotate again. Electrical energy is what I'm looking for. Now I'm talking about the 100 watt lamp, and they told me it's going to happen in 1 minute, which is also something that we can list out. I still have 120 volts as part of this problem because in a parallel circuit, whatever volts you have for the battery is going to be the same volts for every single branch of the circuit. So we could still use 120 volts as part of our as part of the variables that we list if we want to. So V equals 120 volts, P equals 100 watts, T equals 60 seconds. They told me 1 minute, but I know that that's not the SI unit, so I just converted that to 60 seconds because 1 minute is the same as 60 seconds. And I'm solving for W. This is where it really comes in handy to know your units and variables. W here means watts, it's the unit for power. But W here means electrical energy, and that's what I'm solving for. So that brings me to this long formula on the physics reference table. And again, I'm going to be doing W equals, and then I can pick whichever one of these four parts of the equation make the most sense for me. Definitely W equals PT is going to be the easiest because I already know power, I already know time, and that's just going to be the simplest way to do things. So W equals PT, and so I don't need the 120 volts, and that's fine. It can just be extra information. I can plug in my numbers, 100 times 60, and I get 6,000 joules as my answer. Part C says, describe what change, if any, would occur in the power dissipated by the 100-watt lamp if the 60-watt lamp were to burn out. I underlined describe what change because that tells you what you're supposed to be doing for the problem. You're not doing a calculation here. When they say describe, they just want to know if it's going to increase, decrease, or remain the same. So your answer is not a calculation. You can do a calculation to try to figure this out, but you do not have to. All they're looking for is for you to say that it increases, it decreases, or it remains the same. On the physics regents, if they don't ask for an explanation, you do not have to give one. If they just say describe, you're just answering one of these answers. You can explain, but you don't have to in order to get full credit for this question. So I want to know what's going to happen to the power in the 100-watt light bulb if the 60-watt light bulb were to burn out. So we could just mentally cross out this 60-watt light bulb. The whole point of a parallel circuit in general is that each branch does not affect the other branches. So when you get a question like this for a parallel circuit, typically the answer is nothing changes. But let's double check by looking at the formula for power. Power depends on potential difference in current, or it could depend on current and resistance, or it could depend on potential difference in resistance. It depends on which formula you pick, and these are all interrelated anyway. So we kind of want to look at all three of these variables. The power would only change if one of these things changed. So for the 100-watt light bulb, we can imagine if the 60-watt light bulb were to burn out, would the potential difference across the 100-watt light bulb actually change? And the answer is no, because that depends on this battery. A 120-volt battery source means that it's going to be 120 volts for each branch of the circuit. If this one goes away, it's still 120 volts across this branch. That's the nature of a parallel circuit. The current is a little less intuitive, but that is also not going to change. If one of these branches gets burnt out or the connection gets cut, the current does not stop flowing through the other branches, and it will not change the amount that flows through. The resistance also is not going to change. The resistance is based on either, if it's a light bulb, the resistance is just based on which light bulb it is, or if it's a resistor, it's just kind of based on the physical properties of that resistor. So that's also not going to change. So none of these things are going to change, which means that the power stays the same in the 100-watt light bulb. And to get full credit, all you would have to do is say that power stays the same or it doesn't change, something like that.